Lesson 6.3, Mechanical Energy Conservation. Potential energy can be converted into kinetic energy and back and forth. Really? How? Well, think of an object being thrown up. If we throw it up, at the beginning down here it has kinetic energy, but no potential energy, because it's at the bottom. At the top it has potential energy, but at the very highest point it's not moving anymore, so the kinetic energy is zero. So what's happened is that we've changed our kinetic energy into potential energy. The bottom had zero potentially, higher kinetic energy. The top had high potential energy, but no kinetic energy because it stops at the highest point. So our change in kinetic energy equals the negative change in potential energy because they're inverse. Change in means final minus initial. Rearrange this, move all the initials to one side, all the finals to the other side. We end up with a conservation of mechanical energy, which says our final mechanical energy equals our initial mechanical energy. And mechanical energy is our kinetic energy and our potential energy. So all the kinetic energies and all the potential energies. Conservation says that doesn't change, so the final equals the initial. So the conservation of mechanical energy is only true if there's only kinetic and potential energy. And that means the total mechanical energy is constant, such as on this picture. Cart starts at the top, goes down, goes faster, slows down, goes faster, faster, faster. Notice the total energy stays the same until it crashes at the end. Suppose a toy gun uses a spring to shoot plastic balls of 50 grams. The spring is compressed by 3 centimeters. All right, so 50 grams is 0.05 kilograms. 3 centimeters is 0.03 meters. Of course, you have to do some work to the gun to arm it. How much work do you have to do? Well, we need to squish the spring, right? So this will be spring potential energy, which is 1/2 kx squared. K is 2.22 times 10 to the 5 newtons per meter, and the x is the 3 centimeters, or 0.03 meters. Don't forget to square that. You get 99.9 joules. So that's the work we did. Suppose you fire the gun horizontally. How fast does the ball leave the gun? Well, at the beginning, we have the spring with the ball. Afterwards, the ball is just moving. So initially, we have spring potential energy. And that's all the energy we have at the beginning. At the end, we have kinetic energy. But that's it. There's no compressed spring. So at the beginning, we have this 99.9 joules that we got from part A. And at the end, we have 1/2 mv squared. The mass is 0.05 kilograms. Looking for a speed. Half of 0.05 would be 0.025. So divide by that. You get 3,996 meters squared per second squared. Square root that answer, And we'll have 63.2 meters per second for our speed. That's moving very quickly. Now let's suppose we shoot the gun straight up. How high does the toy ball go? So at the bottom, we've got the ball on the spring. So we have spring potential energy. At the top, we have gravitational potential energy. But at the highest point, it's not moving anymore, is it? So on the initial energy side, we just have the spring potential energy. On the final energy side, at the highest point, we only have gravitational potential energy. Well, our spring potential energy was 99.9 joules from part A. The gravitational potential energy is mgh. Our mass was 0.05 kilograms. G is 9.8 meters per second squared, and we're looking for the height. So 99.9 joules equals 0.49 kilogram meters per second squared times height. So we divide, and we end up with about 204 meters for our height. That's rather high. So how do I set this up? I set all the initial energy equal to all the final energy. Initial energy equals our final energy. So the total amount of energy isn't changing. That's the conservation of energy. A 1,500 kilogram car is driven off a 50-meter cliff during a movie stunt. If it's going 20 meters per second as it went off the cliff, how fast is it going when it hits the ground? So we have our car up here, and then we have the car crumpled up down there. So at the start, we have some height. So we have gravitational potential energy, and it's moving, so we have kinetic energy. When it's smushed on the ground, well, actually, we're going to go just as it hits the ground. So at the instant it hits the ground, it's not stopped yet, so it's still moving. So we don't know how fast it hits the ground, but we don't have any more height. The height is 0. So at the bottom, there's no potential energy, just kinetic energy. So our initial energy is going to equal our final energy. So we initially have potential energy and kinetic energy. At the end, we only have kinetic energy. So that's mgh plus 1/2 mv squared, 1/2 mv squared, final and initial. Our mass is 1,500 kilograms. G is 9.8. Our height is 50 meters. Mass is 1,500 kilograms. The initial velocity is 20 meters per second. Mass is 1,500 kilograms. Final velocity is what we're looking for. All right. Run that through the calculator. And on the left, I have 1,035,000 joules, so 1,000,000 joules. On the right, I've got 750 kilograms VF squared. So let's divide. We get 1380 meters squared per second squared equals VF squared. Square root that, and it'll be going 37.1 meters per second when it hits the ground. Which makes sense. It has sped up, and we know things when they fall speed up.